Hello, it's Keith here, and this is the fifth in the YQuest series of 68,000 assembly tutorials, and we're going to be looking at the Genesis today. We're going to be porting YQuest to that system, and we're going to have a look at the game, and we're going to see how we can convert this game to that system. Now here's the game itself. Now this version of the game is using the tilemap, so you can see that the movement is a little bit jerky. We're moving in 8x8 chunks. That's because this is based on the simple series. If you remember, we had a simple example where we had a smiley moving around the screen. But don't worry, we're going to extend this later on. We're going to add hardware sprites and we're going to get some nice smooth movement later. But for now, we're just going to keep things simple and we're just going to use the tilemap to do our graphics. Oh dear, I've died. So anyway, we're not here to see me play the game. We're here to look at how the code works. Let's go over to the code and let's take a look. Okay. So here's the code for the version we're looking at today. This is Gen YQuest. There's Gen YQuest 2, which has hardware sprites. We'll be looking at that another time. Okay, we're going to go over the code today. I'm only going to cover very briefly the parts that are the same as in the previous example. That's the simple series with the joystick example where we were moving a smiley around the screen because I don't want to repeat myself too many times. Now the first thing you'll see here is we've got these collision masks being declared. Well, because we're moving in 8x8 chunks, the internal logic is a bit high resolution, and something that looks like it's overlapping in the logic might not look like it's overlapping on the screen. So we're sort of cropping down the resolution of the calculations so that what looks like is happening on the screen is what's being treated as happening within the collision detection logic, so you don't die when you're not colliding with things. Okay. Then we're defining the size of the screen. Depending on the machine, the screens all have different sizes, so the code can work with all of them. We define our screen size and that changes the logic of the boundaries of the screen and things. We're then defining an area of memory within the Genesis that is going to be used for the game variables. This includes the objects, like the player, the bullets, the enemies, things like that. Most objects are defined by an 8-byte definition, and we're going to see that later on. So that's all of the game variables go there, and that user RAM definition allows us on different systems to have, sometimes it's declared as part of the game code itself because the game's running in RAM, sometimes the game's running in ROM like this and we have to define it in a separate area, so it does vary. We're then defining the ports for the VDP data and VDP control. Here we've got our cartridge header. We've looked at this before, so this is just a generic cartridge header, and this is the start turning off the security chip. We're then defining our screen here, and we're transferring our palette to the VDP hardware. Now the palette is in native format this time, and we can see that at the bottom here. Here's the palette, so that's what we're using there. And once we've defined the palette, where are we? Once we've defined the palette, we're transferring the bitmap data into the tile definition. As I say, all of the graphics in today's example use tiles. Now there's a font. The first 96 characters are a font, and then there are 4 banks of sprites, and there's 16 sprites in each bank, and those are our graphics for the game. So the font is in a native bitmap format. It's not a 1-bit per pixel font this time. So we're defining that, transferring all of that to pattern memory. We're then turning on our screen, and we're using CLDIR to zero the RAM for the game so that everything starts from a known point. We then set up a new game, 3 lives for the player, 0 the score, 0 the level. We then set the sprite back to normal because the sprite might have been changed during the death sequence, and then we are just silencing the sound and clearing the screen, and then we're drawing the title graphic to the screen. Now what we're doing here is we're getting each tile from the definition. There's 1 byte per tile here. If it's non-zero, it's a sprite we're going to show. So we're then calculating the sprite that we want to show here. The getSprite address function calculates the offset jumping over the font and things like that. And showSprite will actually show a tile or a sprite to the screen. I call the tile sprites. In this case, it's sprite from the logic of the game, not a physical hardware sprite. At this stage, it will be hardware sprites later on. We'll look at that in a later lesson though. Okay, so that draws the title screen. We've then got some messages for the screen here. And so here is the start of a new level or a new game. We wait for the fire button to be pressed. We clear the screen, send to the player, give the player some invincibility, and then we initialize the level. So this sets up all the objects for the level of the game. Okay, we've got a loop here. This is a delay loop, and we're then going to read in any key presses that occur. If there aren't any that occur, we're setting this sort of default here. And D2 is going to store the results of any keys that are pressed. And we're using read controls dual to read in the key presses here. Now we're reading in, you can see here, from port A1 0003 here. We do have to set the direction of that port first, and then we're reading in all of the directions and all of the buttons here. Now this is the code from the platform specific series. It's a little bit complicated because we have to send a sequence of signals to the Genesis hardware to select all of the buttons. Now this code is actually excessive. We're reading in far more buttons than this game uses, but the code works, so I wasn't going to change it for the sake of it. So it's a little bit overcomplicated, but that's what's being used there to read in the joystick. Now when the drawing starts, first thing we do is we draw the corner pieces of text, the lives, the score, the crystals remaining, things like that. We then take the player off the screen with the blank sprite routine. You'll notice we point A4 to the player object. Now that is the object that defines the sprite and position of the player. Each graphical object typically in this game uses an object with 8 bytes that define all of the attributes of that object, and that means that we can use the same code to do all of the work. Now, when you hold down a direction in this game, you change the acceleration, but if the code that checked that acceleration worked too fast, you'd accelerate really quickly and quickly lose control. So after a change to the acceleration is processed, there's a timeout, and if the timeout's non-zero, we're going to skip over checking any more directions. So that's what that does there. But then if we are checking directions, we're going to change the Y acceleration and X acceleration of the player. We're just doing a bit test of all of the directions within D2, which was loaded in from the joystick here. Okay. Now, if the fire button 1 is pressed, then we're going to use the fire bullet routine from the multi-platform code. If fire 2 is pressed, we're zeroing the player acceleration, which stops the player dead in their tracks. So handy if you've got 2 fire buttons. Finally, we're setting the key timeout, which is set from D5, which was set if up, down, left or right was pressed. So that's the other part of that timeout. Now finally, we've got draw and move here, which handles the movement of all the objects on the screen and the drawing of all the objects, including the player. We then loop back up here for the next iteration of the main game loop. So that's the main game loop there. Okay. Clear screen here will clear the entire tile map. We're setting the base offset of the tile map here, and then we're just going to write zeros to all the tile numbers because 0 is the space in our font, so that will effectively clear the tile map. And remember, the tile map's the only thing we're using in this example, so we're not using any sprites yet. Okay, so our print character routine, this will again use the tile map and it will print the characters from that font. Now the font has no characters below 32. No characters, not now characters, no characters. So we're subtracting 32 from the character we're passed, and that will then be the sprite number we want to show at the XY position of the cursor. We're using the show sprite routine because, say, the font is in the same format as the sprites, the same bitmap format, so very handy. Okay, now blank sprite will use the object passed in A4, and this is the object that we want to draw to the screen, or in this case remove from the screen. Now we're checking something known as the collision program, which defines how the object interacts with the world. So a certain collision program will mean that the object can hurt the player, but a collision program of 255 means the object was never initialized, and 254 means it was an object but it's been killed and it's not back yet. So if the object collision program is over 250, we don't want to clear it off the screen because it doesn't exist yet. So we're just skipping over then. But if we do need to remove it from the screen, then we're using sprite 0, which is the space again, and we're going to use that to show the sprite to the screen. Okay. Now get sprite address, this is used by the calculations, and in this case it's calculating the tile number that we want to show. So it's used for the graphics, so we add 96 to jump over that font. We then use the sprite frame, which is the frame of animation, and we multiply that by 16, effectively selecting which bank of sprites we're showing, because there's 4 in total, 0 to 3. And sprite frame automatically sequences between those 3 for the animation. Only simple animation, but it's not so bad. Show sprite will show an arbitrary sprite to the screen. We specify the sprite number and the X and Y position just passed in the registers. We've got do get sprite object, however, and this takes the settings from an object in the same way as blank sprite did. So it uses A4 and it's reading the sprite number, the X and Y position from A4. It's multiplying up the X and Y position for the correct tile position on the screen, and then we've got this rather nasty formula here which calculates the memory address of the tile position in the screen. That was all covered in the simple series. I'm not going over it again because it's confusing. And then finally we're setting the tile in VRAM, so we're sending the address of the VRAM for the tile we want to change and the new tile number in D0 here, and that will show the tile to the screen. Okay. Define tiles, this is used by the startup routine, and it just basically transfers all of the tile data to VRAM using this prepare VRAM function, which again is a little bit overcomplicated because of the nature of the VRAM selection routines. Read controls dual. As I say, this is copied from the platform specific series, and this reads in all of the joystick keys, including the ones we don't need, but it will read them all in and it will store them in a single register for us to make things a little bit easy for us. Wait for fire. This checks if the player has pressed and released fire. This is a sort of debouncing thing so that we can start a new level, and if the player's been holding down fire for a long time, we'll actually wait for them to release before continuing to the next level. So that's what that does. And then we've got our bitmap data here, our palette, and finally the VDP settings here, which define the layout of the screen. At the very bottom here, we've got our multi-platform code and the definitions that are common to all of the versions of this game. So there we go. So that's what we've got for today. As I say, this is hopefully something you could maybe build on to make your own simple game. Now, I know that the movement in this version isn't very good. It moves in these 8x8 chunks, but as I've said a few times, I think if you're starting out writing your own little programs, that's a sort of reasonable place to start from. You know, that shouldn't be it should be enough for you to make a nice game, and it makes things a lot easier for you if you're just using the tilemap. But don't worry, because we're going to move to using sprites later on with the second version of this game, and to be honest, I was able to convert this to the sprite version in well, I think probably a couple of hours only. It was very quick, and once I've got the first few working, porting, I've done this for the X68000, the Neo Geo and things, and once you get used to it, you can do it very quickly. So the point I'm making is if you design your game well, even if it only uses tilemap at the start, you can then start to extend it and use hardware sprites later on. So I think the tilemap is a nice place for you to start with, just to get your little game started off. Anyway, you can go ahead and download this sample from my website, and as I would say, you can use it in any way you want, and if you somehow manage to make a commercial game out of it, I don't care. Good luck to you. You don't need to give me credit even. So do whatever you want with it. Anyway, whatever you do, I hope you enjoy your Genesis programming, you have a lot of fun and success with that. If you've liked this video, please like and subscribe. If you like the videos, it encourages YouTube to recommend them to other people, and if you subscribe, it encourages me to make more videos, so everyone's happy. Thanks for watching today, and goodbye.